Naresh, working in the assistant professor in EC department. And today's topic is effect of coupling and bypass capacitors on CE amplifier. So in this session, we are going to discuss what happens while we are placing the capacitors at the input side as well as the output side on a common emitter amplifier. So before this, first we need to discuss what is a CE amplifier. So how it performs the amplification process by using this common emitter configuration. Then we will discuss what happens while we are placing these capacitances at the input and output side. So generally we have two types of the transistors. One is NPN transistor, another one is PNP transistor. And we know that based on the construction, we have the two junctions. So one is emitter base junction, another one is collector base junction. And we have the modes of regions when both these junctions, means emitter base junction is a forward bias and the collector base junction is a forward bias. It acts as a saturation mode, and when both the junctions are reverse bias, it acts as a cutoff region. When emitter base junction is a forward bias and the collector base junction is a reverse bias, then it acts as a active mode configuration. So to satisfy the amplifier means to transfer the low resistance input device to the high resistance output device. So we need to make the transistor should be in an active region. So in this active region, the transistor acts as a amplifier, means amplification process. So let us consider we are going to design a common emitter configuration. So in this case, this is base and emitter collector, and we know that. So to satisfy the amplification principle, we need to make the emitter base junction should be forward bias, and we consider the type of the transistor is NPN transistor. So based on the polarity of the materials, then we need to make this junction should be either forward bias or a reverse bias. Let us consider and the emitter base junction. So base is made up with P-type material. Hence, it is connected with the positive pole of the battery with respect to this emitter. Hence this VBB positive pole is connected to base of this NPN transistor. Then negative pole of this biasing source is connected to emitter side there. And now this emitter base junction becomes forward biased. And due to this biasing, we are observing the potential difference between base terminal and emitter terminal is represented as VBE. So this is the potential difference between base and emitter. Similarly, then to satisfy this amplification principle, and we need to make this collector base junction should be reverse bias. So let us consider this is a collector. The collector is made up with N-type material. So hence N should be connected to positive pole of the battery. This is positive pole of the battery. Hence this collector base junction becomes reverse bias. So now under this biasing configuration, now it is acts as a amplification process. So that is the reason I mentioned this point. The emitter base junction is a forward bias by the power supply VBB, and the collector base junction is a reverse bias by the power supply VCC, so that the transistor remains in the active region through its operation. So in that, again, we know that to satisfy the amplification principle, we need to maintain a proper Q point to step, and based on the proper Q point, we are providing the amplification process. And if you observe, there are the capacitance we have. The two capacitances here, one is C1 capacitance and a C2 capacitance, and one is connected across the input side and one is connected across the output side. Then one more is if you place this to stabilize or to to maintain a proper Q point irrespective of the temperature variation parameters like beta or a reverse saturation current or your input current that is a base current. To stabilize that, for that case, we are going to use that self bias configuration. So in the self biasing configuration, we use that emitter resistance, and across that emitter resistance also we use that capacitor. Then we'll discuss later what is the importance of those capacitance while placing the input and output side. So from this, let us consider. So in a previous case, if you observe, we have in this circuit we have the two DC sources. One is a VBB, another DC source is represented as a VCC. To replace these DC sources with only one DC source, hence this circuit diagram I'm redrawing. So two voltage sources are replaced with only one voltage source, that is represented as plus VCC. And again, if you verify, means the emitted base junction we need to maintain as a forward bias. So hence, base is a biased with the positive pole of the battery through the biasing resistance RB. Hence, the emitted base junction becomes forward bias. And similarly, we need to satisfy the collector base junction is a reverse bias. So for this case, the collector terminal is again biased with a plus VCC. Hence, so this is the N-type material. So here N is connected to positive, means this particular junction becomes reverse biased. And again, we are placing these capacitances C1 and C2. And in generally, we know that the capacitor allows only the AC signal and it attenuates the DC source. And before this, now we need to identify the DC biasing conditions as well as the AC biasing conditions. So under this point, when if there is no signal passing through, let us consider under the absence of given AC signal. So let us consider only the DC conditions. So we know that what happens under this DC condition. So the capacitances acts as a blocking open circuit condition. So hence the C1 and C2 acts means the two capacitors. What are the capacitors we used here? The C1 capacitance and the C2 capacitance. These two are acts as a open circuit. So means the circuit looks like means, so it is represented as RB, and it is again biased with a collector resistance RC and RB. Now this is open circuit. Now this is emitter is connected to ground. This potential is represented as VCE, and here this potential is represented as VBE. This is the base node, and it is connected to a DC biasing source, so it's a VCC. So from this, and we need to maintain. So why? Because we know that from the CE amplifier, the collector current expression is represented as beta times of IB plus 1 plus beta times of IC naught. So in this case, now we need to maintain how much base current is produces with respect to these biasing conditions. Hence, from this equivalent circuit, now we need to find out the base current. So hence, apply the KVL at this input loop to identify the base current. So generally it is a V by R, means we have the two potential nodes. One potential node is a VCC, another potential node is a VBB. Hence, the difference between these two nodes is represented as VCC minus VBE across this resistance, that is RB. Hence, VCC minus VBE by RB. So in generally, the VBE is approximately equal to cut-in voltage of that particular junction. And we know that the cut-in voltage is either 0.7 or 0.3. So this is 0.7 for silicon and 0.3 for germanium. So hence, let us assume that this VCC is a much greater than of VBE parameter. Hence, I neglected this VBE parameter ideally. So hence, IB is represented as VCC by RB. Now generally we know that IC is equal to beta times IB. You can substitute this IB to identify the collector current. Now, to identify this output voltage, now again apply the a KVL at output side. So means we can write this one. Means how to write this one means in this case VCC is equal to IC times of RC plus VC. So from this we can write this VC is equal to VCC minus IC times of RC. So hence the VC is equal to VCC minus IC times of RC. Now coming to here, so under this condition, what happens when a sinusoidal signal is passing through this one? So let us take your given input signal, and it should be means we have some node voltage here. Your applied input voltage must be greater than of this VBE voltage. Now under this condition, your emitted base junction becomes forward bias. If it is a forward bias, now again due to this condition already the collector base junction is a reverse bias. So here we observe that the VCE is equal to VCC minus IC times of RC. So hence it allows maximum. Now we know that IC is equal to beta times of IB, and then again we observe that IB is equal to VCC by RB. So under this condition, what happens? It is IB is a maximum when IC is also maximum. So means your IC collector current, if IB is increases, the collector current is also increases. If the collector current is increases here, VCE is becomes reduces. So hence VC becomes a very large current, and this VCE becomes a negative. So hence it acts as when a positive peak is applied, then it produces a negative amplitude at the output side. Similar to that, when a negative peak is passing through this amplifier circuit, so what happens? Emitted base junction is a reverse bias. Now, during this cycle, during the negative peak cycle, emitted base junction becomes reverse bias, and already collector base junction is a reverse. Both the junctions are reverse bias. We know that it acts as a cutoff region. So hence, and there is no flow of collector current, IC becomes zero, hence VCE is approximately equal to VCC. So from that point we observed here, so during this positive portion output becomes a negative peak, and then during the negative off cycle the V0 is reached to VCC, so hence it allows this one. So from this we can say that for this CA amplifier, the output is 180 degrees phase shift with respect to the given input signal. So for this case, now we are going to discuss what happens due to these capacitances. Let us say we have the three capacitance C1 and C2 and C3. So here the C1 and the C2 is acts as a coupling capacitors. So the C1 and the C2 capacitors acts as a coupling capacitors, and the C3 is acts as a bypass capacitor. So means what is the function of this bypass capacitor? The bypass capacitor is a capacitor that short the AC signal to the ground, in that if any AC noise presents on a DC signal, that should be removed to produce a much clean and pure DC signal. So a bypass capacitor is basically bypasses AC noise that may be on a DC signal, so filtering out AC so that it clean and pure DC signal goes through without several AC ripple. So in this case, now the C3 is here, it is acts as a bypass capacitor. And let us take, if any DC signal contains a AC noises or AC ripples, so if we are going to make that AC signal is reached to ground, so we know that capacitor is allows AC signal and it blocks the DC source. So that is the reason. So while passing the DC signal, it contains any AC harmonics. That AC harmonics is passing through this capacitor. Means, so what happens here with the capacitor, at this AC harmonics, the capacitor acts as a short circuit. So hence, whatever the noises is there in the AC ripple, that should be taken to the ground potential. A complete DC signal is leaving at this point. So hence, the complete DC signal is passing through this RE to stabilize the always the emitter base junction is forward bias and collector base junction is a reverse bias irrespective of the variations in the temperature. So similar to that, and yeah, now what is the importance of this coupling capacitor means? So we need to intersect the means. So we need to intersect the AC signal is superimposed on a DC source. So we need to superimpose this AC source on a DC signal. So we need to connect a capacitor. So here, what happens? The C1 and C2 here, C1 and the C2 capacitors are acts as a coupling capacitors. C1 and C2 is acts as a coupling capacitors. So why be that? We need to interconnect the AC source to an a superimposed with a DC source. So we have there are some DC source condition to maintain a proper Q point. For this case, the signal is passing through this node. It should be superimposed on the DC source. For this, we are connecting this one to the base of transistor. So hence, under this condition, whenever the AC signal is passing through the capacitor, and this capacitor is acts as a short, means it allows the frequency signals. So under these conditions, so this capacitor is acts as the interconnecting between this AC source to the DC biasing node. So hence this is called as a coupling capacitor. So by using this C1 capacitor, we are superimposing this AC signal on a DC source. And similar to that, we need to measure the output parameter across the load resistance. So hence under this AC signal, so again the C2 is also acts as a short circuit. So whenever it is a short circuit, this RL is connected to this output node. Under this condition, so this RC is connected with the RL at the output side. So under this condition, from this, the equivalent AC resistance is a parallel combination of your collector resistance and load resistance. So hence this C1 and the C2 is acts as a coupling capacitors and the C3 is acts as a bypass resistance. So now, if you are using what happens when we are using this emitter bypass resistors? So we observe some of the amplifier analysis by using the small signal model. So when we are using this CE amplifier with and without emitter resistance, and in that from that amplifier analysis by the low frequency analysis, just I'm recalling here the input impedance side without emitter resistance. The input impedance is represented as only the HIE. And similar to that, when we are placing the emitter resistance across the emitter terminal, then we observe that the total input impedance is increased, means HIE plus 1 plus HFE times of R means. So if then what happens? Why this input impedance is increases? Then what happens if the input impedance is increases? So from that we know that from the common emitter amplifier, IC is represented as beta times of IB. If any temperature parameters are changes, or beta is the changes, or VB is the changes, or the reverse saturation is the current is the changes, it affects the collector current. So that is the reason. So what I means, we need to compensate this one. To compensate this one, we are placing the emitter resistance. Means if you are placing this emitter resistance, it increase the ZI, means input impedance, RI or ZI. If it is increases, means that base current is decreases. If the base current is decreases, the collector current is also decreases. So means by like this, it compensates this one. How much collector current is changes with respect to the temperature dependent parameter. The same factor should be compensated by adding this emitter resistance across the common emitter amplifier. So that is the reason why if you observe this one, the ZI is represented as HIE plus 1 plus HFE times of R. So that is the reason when an emitter resistance is added to a CE amplifier, the voltage gain is reduces as well as if the input impedance is increases. So whenever the bypass capacitor is connected in parallel with the emitter resistance, the voltage means here, while adding this one, what happens means, due to this overcome means, we observe here, we are compensating the collector current, but the drawback is voltage gain is reduces means, so the voltage gain is reduces means amplification factor is reduces. So generally we know that V naught is directly proportional to A times of VI in amplification factor. And here this is indicates that the voltage gain and amplification factor. So based on this, while we are adding the emitter resistance, now it reduces this voltage gain. So hence amplification process is reduces. So to overcome this one, we are placing a bypass capacitor is connected in parallel with the emitter resistance. Then it improves the voltage gain of the C amplifier. So that is the reason. If the bypass capacitor removed, the extreme degeneration for this amplifier cycle and the voltage gain will be reduced. So that is a reason to improve the voltage gain and to compensate the change of collector current with respect to this temperature parameters. Then we need to use this bypass capacitor. So if there is no bypass capacitor, but it stabilizes the viewpoint, but the drawback is to reduce the voltage gain of the amplifier. So that is the reason to maintain a proper voltage gain and to maintain a proper Q point for common emitter amplifier. So we need to use a bypass capacitor. So by using this bypass capacitor, it stabilizes the means it maintains the proper voltage gain as well as the proper Q point. So let's see one a simple problem. So here for this case, so let us consider here. So for the C amplified shown in below figure, find the percentage change of the collector current if the transistor with HFE is 50 is replaced with another transistor, the HFE is 150. Assume the VBE value is 0.6. So these are the given specifications. They are given that voltage divided by S network. That is R1 is a 25 kilo ohms, R2 is a 5 kilo ohms, and RC is a 1 kilo ohm, and RE is a 100 ohms. Now first we need to find out, due to this voltage divider network, we need to find out this equivalent base resistance. We know that the voltage across the base is represented as so R2 divided by R1 plus R2 into VCC. They can substitute this R2 and R1 wells means what is the R1 R2 value of R2 value is a 5 kilo ohms. Otherwise means we need to find out the voltage means I into that VB is equal to I into R2, where I is equal to V by R. V means this is VCC, so hence or VBB. So VBB by R means total resistance R1 plus R2. Now you can substitute here that VB becomes VBB by R1 plus R2 into R2. Hence, this factor is divided by R2 by R1 plus R2 times of this VBB. That is equal to VBB means you can take this VCC otherwise. So that is the reason we observe that here VBB is equal to, in the place of that one, I use this VCC means. So this point, so this I consider here. So otherwise you can consider this is VCC. Now it becomes this is VC. So hence means that is 12 divided by R1 plus R2 means 25 kilo ohms plus 5 kilo ohms into 5 kilo ohms. So that gives a 2 volts means the voltage across the base is represented as 2 volts. But again, if you observe this one, it is represented as VBE means what is the meaning of VBE? VBE means the potential difference between VB and VE. So from this we can write VB is equal to VBE minus VE, or if you want to find out the VE is equal to VB minus VBE. So hence, so here I am going to write how much we are going to find out how much voltage drop will be generated while you are placing this emitter resistance. Hence, so I use this VE is equal to VB minus, from that relation we observe that the potential difference between the VB and the VBE. So VB we observe the 2E And in the problem statement, VB they given that 0.6. So hence 2 minus 0.6, that is equal to 1.4 volts. Now again, so now we need to calculate how much emitter current is the flows. So across this transistor, so means I is equal to V by R, means V by RE. So from that, so V is we observe that 1.4 volts and R is given at 100 ohms. Hence it gives that the emitter current is 14 milliamperes. Now again, from that we identify that, so this is beta is equal to 50. From that IB is equal to IE by 1 plus beta. So IE value is here, they given that 14 milliamperes, 14 to 10 power minus 3 by beta is a 50, so hence 1 plus beta is nothing but, so this is 1 plus 50, then it becomes 14 into 10 to the power of minus 3 by 51. That gives that 274.5 microamperes. So this is the base current value. IB is equal to 274.5 microamperes. Now we need to calculate so the collector current. So we know that from the common emitter amplifier, the collector current is represented as beta times of IB plus 1 plus beta times of IC naught, where IC naught is a reverse saturation current. So the reverse saturation current is very very small, hence we neglected that one. So hence IC is approximately equal to beta times of IB. So from this, now we need to identify that in the problem statement they given that, so to find the percentage change in the collector current if a transistor with HF is 50 replaced by another transistor is 1. It means we need to find how much collector current is the changes when the beta value or the current gain of the transistor is the changes. So first we need to find out the currents for when HFE value is 50 and when HFE is 150. So from this analysis, so we observe that the collector current is approximately equal to beta times of IB. So here we observe IB is 274.5 microamperes. Hence, the IC1 value is equal to beta times of IB. So beta value is 50 and IB value we observe that 274.1. So this is the case for when I consider that beta is a 50. So then the IC1 value is 13.725 milliamp. Now we need to calculate when beta is a 150. Now we need to first identify that IB. So what is the find the IB? We observed IB is equal to IE by 1 plus beta. So hence, so IE is we observed 14 milliamperes by, and this is so 14 into 10 to the power of minus 3 by 1 plus beta value is I taken as 150 here. So under this count, the base current is, so the base current is 92.715 milliamperes. Now we need to calculate by using this standard expression. The IC is equal to beta times of IB. So now I'm going to calculate how much collector current it produces with respect to this beta value. So here a beta value is 150 and IB value is 92.715 into 10 to the power of, this is micro, into 10 to the power of minus 6, then it becomes 13.907 milliamperes. Now we need to identify how much factor the changes, the percentage the changes. So we have the to calculate this the change of percentage. So IC2 minus ICE by IC1 into 100. So this is means we observe this. So IC2 value is 13.907 milliamperes minus, and means the collector current again here with respect to the emitter, that is 13.725 into 10 to the power of so means 10 into 10 to the power of minus 3, then divided by again IC1 is 13.725 into 10 milliamperes. Then we need to change the percentage change, so that is the reason. So it produces 1.326 percentage is a changes when the beta is a change from 50 to 150. So up to this point in this session, we observed that what is a amplifier, common emitter amplifier, and by for that common emitter amplifier, we use that a coupling capacitors as well as the bypass capacitors. So first in that we observed that what is the CE amplifier response, and from that we observed that common emitter amplifier produces a 180 degrees phase shift with respect to the input signal. Then after that we discussed that what is the importance of coupling and bypass capacitors. And the coupling capacitors can be used to interconnect the means a AC source to the input side as well as the output side. The load resistance is connected to the collector side. Then bypass capacitor can be used to improve the voltage gain. So means that so if there is no bypass capacitor for a CE amplifier, so while you're adding the emitter resistance across the emitter side, it reduces the voltage gain, but it increases the stability, but it improves the stability factor. To compensate this with the reduction of the voltage gain, then we are placing a capacitor across the emitter side. That capacitor is called as a bypass capacitor. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.